Dear audience, I'm Qinzi. It is my honor to present a communication-efficient Byzantine-tolerant distributed machine learning algorithm in single-hop radio network named Echo-CGC, together with Professor Louis Tseng. Our model focuses on the synchronous stochastic gradient descent algorithms. In a gradient descent setup, there is a cost function Q, and the goal of the algorithm is to output an optimal parameter that minimizes the cost function. For a traditional single-device gradient descent algorithm, in each run, the device computes the gradient of Q and performs the gradient descent according to this equation. However, the cost function is typically computed from the data. So as the data size gets bigger, it becomes almost impossible to run this algorithm on any single device. As a solution, distributed machine learning is designed to handle a large amount of computation over big data, which is difficult to be trained on a single device. Our distributed learning algorithm works on a parameter server model. There is a centralized parameter server. In each run, the server distributes the computation task to all workers. And to be more specific, each worker has its own local dataset, which is assumed to be a minimal batch, that has the same distribution as the entire dataset. Each worker then computes the gradient using its local dataset, which is a stochastic estimate of the true gradient. After the workers finish the computation, the central server will then collect the results and use them to perform the gradient descent. And we assume this process is done in synchronous runs. So ideally, the distributed version of the gradient descent should naturally be the following equation, which is subtracting the current parameter with the sum of all aggregated gradients. However, in the real world, such simple aggregation rule is vulnerable to malicious attacks. For example, if there exists an omniscient adversary that knows all the gradients, then it can hack in one worker and manipulate its gradient such that the sum is always 0. This certainly prevents the algorithm from converging. So the existence of such an adversary raises the need for a fault-tolerant distributed learning algorithm. In our model, we assume the fault adversary has the following properties. First, we assume that the central server is always fault-free. Otherwise, without a reliable server, it is impossible to learn anything. And second, we assume that among all N workers, there are at most F Byzantine faulty workers. All other workers are called fault-free workers, and they will honestly follow the algorithm. In later section, we will discuss the upper bound of this constant F. Faulty workers can behave arbitrarily. For example, they can send arbitrary message, or they can act as they are crashed. However, since we assume the algorithm is synchronous, the server can distinguish the faulty workers if they act as crash workers and do not return anything within a run. And finally, we assume that the adversary is omniscient, so it knows everything about our algorithm, as well as the information in every execution. However, it can only manipulate the faulty workers. In our model, we assume the standard single-hop network that ensures the reliable local broadcast property. This assumption follows from the prior works, such as Binary and Bydius on reliable broadcast in a radio network, and Alistair and his groups securing every bit authenticated broadcast in radio networks. To be more specific, the reliable single-hop network ensures the following properties. First, the network is fully connected. In other words, each pair of the workers are within the communication range of each other. Second, the network is reliable, which implies two things. First, each worker has a unique identifier, and workers cannot lie about their identities. Also, the broadcast message of each worker is identical. In other words, if one worker broadcasts some message, then the server and all other workers will receive the same message. And finally, we assume that there is no message collision. When one worker broadcasts, all other workers will receive it before any other worker broadcasts another message. To be more specific about our broadcast model, in each run there are n time slots, and in each subslot I, only worker I is allowed to make a reliable broadcast. As this graph shows, in the first slot only worker 1 broadcasts, and so on. Since there is no message collision, the server and other workers can always receive the message sent by worker I by the end of time slot I. There are many related work on Byzantine-tolerant distributed machine learning. However, to the best of our knowledge, none of the prior works have considered the communication cost from workers to the server. Chen and his group, and Su and Vidya, proposed fault-tolerant distributed algorithms using geometric median as their aggregation rule. Venture and his group proposed the crumb algorithm, which chooses the gradient with minimum sum of the closest Euclidean distances. And Damaskinos and his group extends this result to the asynchronous model. Xie and his group proposed Zeno, which only requires one fault-free worker. Gupta and Vaidya proposed comparative gradient clipping filter, and this CGC filter inspires our work. Despite their differences, all of these algorithms have relatively large communication complexity. Therefore, the main focus of our algorithm is to reduce the communication complexity of the messages. The prior algorithm required every worker to send the entire gradient to the server. So if the data is in D dimension, the message is of the order of big O of D. In practice, D can be extremely large. For example, it can be about millions. This can be relatively expensive. On the other hand, our algorithm does not require all workers to broadcast the full gradient. Once a worker meets some echo condition, it can instead return a reduced message whose order is about n, where n is the number of the workers, and it is far less than D. In practice, n is about hundreds. Now we formally present our algorithm Echo-CGC. This algorithm works in iterative runs. In the arbitrary run T, there are 3 main phases. The first phase is a computation phase. And in a computation phase, the server distributes the computation task and broadcasts the current parameter Wt to workers. The workers then compute the estimated gradient G sub k, which is a random approximate the true gradient of the cost function Q. The next phase is the communication phase, and this is also the main novelty of our algorithm. The communication phase is divided into n subslots. Each worker proceeds to broadcast its estimated gradient in the order of the identifiers. In time slot I, worker I first checks its echo condition and broadcasts its gradient to the server and all other workers. We'll discuss this echo condition on the next page. For example, in time slot 1, worker 1 always broadcasts its full estimated gradient G1 to other components. Meanwhile, every worker I has a local memory that stores necessary received gradients, which is denoted as R sub I. Upon receiving a gradient from worker I, node J other than I will check whether the received gradient is in the span of R sub J, the set of all stored gradients. If it is not in the span, then worker J will store this new gradient in R sub J. This mechanism ensures that R sub J is always linearly independent. So if we treat R sub J as a matrix whose columns are the stored gradients, then the matrix always has a more parallel pseudo-inverse. Now we discuss in detail the echo condition. At the beginning of each time slot I, worker I will check its echo condition, and if this condition is satisfied, then it will broadcast a reduced message instead of the entire gradient. Recall that R sub I is the setup of the stored gradient by worker I. The intuition is that if there exists some gradient in the span of R sub I that is close enough to the estimated gradient G sub I, then the worker can return the server an approximate gradient in the form of a linear combination of the stored gradients in R sub I. For example, let radius r be some threshold distance, then the echo condition is equivalent to checking whether the span of R sub I intersects with the ball with radius r centered as G sub I. And in practice, we implement this condition by first finding the shortest distance from G to the span of R, and then check whether the shortest distance is less than the threshold radius r. And recall that in phase 1, our algorithm guarantees that R sub I is a linearly independent set. So if we write R as a matrix A, then A has more parallel pseudo-inverse. And this also implies that the equation AX equals to G has a more parallel least square solution, which is the pseudo-inverse multiplied by G. In other words, the vector delta G sub I has the shortest distance from the span of R to the gradient G, and the echo condition is actually equivalent to check whether the Euclidean norm of delta of G is less than the radius r. As a brief conclusion, if worker I satisfies the echo condition, then it can send the reduced message X, which is the least square solution on the previous page. And intuitively, the worker returns an approximate gradient in the form of the linear combination of the gradients stored in R, and X is equivalent to the vector of the coefficients of the linear combination. Our reliable single-hop network ensures that the server and the workers have the same stored gradients. Therefore, the server is able to recover the approximate gradient using only the coefficients. Now, let's look at the size of the reduced message. We know the size of the set R sub I is at most n, so the matrix is a at most d by n matrix, and the pseudo-inverse is an at most n by d matrix. Also, the gradient G is a d-dimensional vector, so altogether the reduced message X is an at most n-dimensional vector. Since d can be as large as millions and n is in practice about hundreds, the complexity of the reduced message is almost negligible compared to the original gradient. In the final aggregation phase, the central server applies the comparative gradient clipping filter, the CGC filter, to all received gradient. Given a threshold gradient G bar, the CGC filter scales down the norm of a gradient G sub k to the norm of G bar if G sub k has a greater norm. Otherwise, it just keeps G unchanged. And we choose the threshold of the CGC filter as the f plus first largest gradient. In other words, we scale down the f largest gradients by the CGC filter. For example, in this graph, if we suppose f equals 2, then the threshold gradient is the highlighted one. And if we apply the CGC filter, then the two largest gradients are scaled down. The intuition behind the CGC filter is that we want to keep the aggregated gradients in the correct direction. there are at most f faulty gradients. So in the worst case, we may assume that the faulty gradients have the largest norms. For example, in this graph, the red vector represents the faulty gradient, and the green vector is the true gradient of the cost function. Without filtering, the faulty gradient can be arbitrarily large, so the overall aggregation of the gradients might be in the opposite direction to the true gradient. Therefore, we want to reduce the negative impacts of the faulty gradients by scaling down their norms. And we actually proved that as long as there are sufficient fault-free workers, the overall direction is always close to the true gradient. And finally, the solver performs the gradient descent using the sum of all CGC filter gradients. And this concludes round T. In our full paper, we proved the convergence of our algorithm under several standard assumptions that are common in prior works. First, we assumed that the cost function satisfies some nice properties. Q is assumed to have Lipschitz continuous gradient with the Lipschitz constant L, and it is also assumed to be strongly convex with convexity constant mu. Also, we assume that the local dataset of each worker is distributed identically and independently from the entire dataset. Therefore, for all fault-free workers, the expectation of the estimated gradient equals to the true gradient of the cost function in each round. And moreover, the variance of the norm of the gradients is assumed to be bounded. Under these assumptions, we determine an upper bound of the number of faulty workers that is sufficient to the convergence of our algorithm. We prove that if the fault tolerance f over n is less than the bound 1 over 4L over mu, where L and mu are the Lipschitz constant and the convexity constant, then the algorithm Echo-CGC is guaranteed to converge. Finally, we present the performance of our algorithm. We computed a theoretical upper bound of the ratio of the reduced complexity to the original complexity. This bound is a complicated function and is dependent of 4 variables, and we plot the relation between the bound of the ratio and each variable. The first and the most significant factor is the variance sigma. In the first plot, we fix other 3 variables and plot the upper bound as a function of variance. We can see that the upper bound is almost a quadratic function of the variance. When the variance is relatively small, our algorithm performs well. The second factor is the cost function. To be more specific, the ratio is dependent to the ratio of the convexity constant to the Lipschitz constant. As the ratio mu over L comes closer to 1, the upper bound of the reduced complexity decreases. Third, there is a trade-off between the reduced complexity and the fault resilience. As the fault tolerance approaches the sufficient upper bound, which is 1 over 4L over mu, then the upper bound of the complexity blows up. And when the fault resilience is relatively low, the complexity is guaranteed to be low. Finally, we plot the upper bound of the reduced complexity against the number of the workers n. As the graph shows, the complexity increases linearly with n, and the slope is relatively small. Therefore, we can conclude that n is not a significant factor of the complexity. As a summary, we present our Byzantine-tolerant distributed machine learning algorithm that incurs lower communication complexity in a single-hop radio network. Our algorithm is inspired by the CGC filter, but we devised new proofs to handle the randomness and noise introduced in our mechanism. there are two interesting open problems. First, our current model assumes a single radial network. A natural extension is to extend the current algorithm to the multi-hop radial network, where the network is no longer necessarily fully connected. Second, our current echo condition checks whether a vector is close enough by comparing the Euclidean distance to a certain radius threshold. So an interesting problem is that whether there exists a more efficient mechanism for constructing echo messages. For example, can we use the angle between the computer gradient and the store gradient instead of the distance? And that's all of our result. Thanks for listening.